With the expected population growth to continue during the 21st century, it is necessary to ensure a sustainable development pattern for urban settlements without compromising the resources and land use for future generations. Many of the already existing towns and cities with consolidated infrastructure will need to upgrade and adapt to these new challenges, while new urban settlements must be carefully planned. As a result, it becomes crucial to have extensive knowledge of the previously existing man-made infrastructure, as well as the morphology and geology of the site. Furthermore, by increasing the density of cities and consequently the occupation of space both over and underground, we will need to know these details with greater precision. Currently, the most widely used methods of studying the underground of cities are drilling boreholes or excavating trenches, which come with the disadvantages of limited horizontal and vertical coverage and the potential to disrupt building foundations. Indirect methods, such as seismic reflection and refraction, often come with the perception of vibrations by residents and the vulnerability of older or poorly constructed buildings. In order to address these limitations, the usage of muon tomography, or simply muography, appears as a potential non-invasive candidate, as it gives an unprecedented upwards look into the hidden spaces beneath our cities. It functions similarly to an X-ray of the city, as muons originated by cosmic ray showers have great energies and are able to cross the atmosphere and man-made structures and even penetrate several meters underground. Detectors located below the site being studied record the number of muons that cross them. These detectors are made of various planes subdivided in smaller pixels to allow the study of their trajectories. When muons cross the material, it is ionized and creates an electric discharge that can be collected by the electronic components, as well as locating the pixel where it took place. Muons lose on average 2 MeV per gram per square centimeter, meaning that their energy loss in materials depends on the length traveled inside them and also on their densities. Therefore, not all muons that reach the surface will also reach the detector, and based on the number of muons received from each direction, which is sensitive to the shape and density of the structures above, it is possible to make a low-resolution reconstruction of these structures. Muography also takes advantage of the natural source of muons originated in cosmic ray showers, resulting on an average of 10,000 muons per square meter per minute at surface level, which mitigates the limitations of always having to place the detectors below the object of study. My work will focus on studying the possibility of using muography along the drainage tunnel currently under construction below Lisbon from Monsanto to Santa Apollonia, providing a valuable study case of the cross profile of the city, intersecting different geological formations and providing access to the study of known over and underground infrastructure. In urban settings, muon tomography must take into consideration both natural and man-made structures, over and underground. As a result, it is important to establish the significance of the existence of these elements in the collected data, meaning that studies must be done to characterize how much each of these variables will influence the experimental results. This will therefore be the focus of my project, under the supervision of Sofia Andringa and Bernard Tomé, with the objective of optimizing the data acquisition strategy and processing chain to allow for this implementation.